Okay, so thank you very much for the opportunity to speak. And so today I'm going to tell you about a program in trying to better understand the physics of collisions, such as this, at colliders, in terms of certain ideas from Lorentzian conformal field theory, in particular this notion of conformal colliders, which I'll explain later. And so I should just say that for time, I'm going to focus just on the case of the LHC. And so there's a lot of work which I will not cite properly throughout, and for that I apologize. So if we consider a collision of the LHC, you get all these sprays of tons and tons of particles. And so the classical way of kind of thinking about them is to group them into these cones, which are referred to as jets. And so these can be thought of as just kind of blobs of energy going in some particular direction. And so they just have a total energy and a direction. And there's been a huge amount of progress in computing these jet cross-section using advances in scattering amplitudes. And so in the last maybe 10 or so years, there's been a big push to try and better understand the actual distribution of energy inside jets. And so to understand, for example, the statistical properties, for example, as shown here in this 3-point correlator. And so you can ask why you would want to do this apart from intrinsic interest. And so the original idea which motivated this, which goes under the name of jet substructure, is that if you produce some new physics in your collider, for example, this Z prime particle shown here, and if you just see the hadrons flowing out into your detector, the only way that you can see that something interesting happened is by studying the detailed distribution of energy which arrives in your detector. And so this was kind of introduced around 2008 and really made an explosion of interest in trying to better understand the properties of jets in QCD. And in particular, introduced a huge number of qualitatively new ways to study physics at the LHC. And so this is by now an extremely well-developed field. So there's hundreds and hundreds of searches at CMS and Atlas which use all of these techniques. And so it's had a huge impact and also very nice synergies with machine learning. And in fact, it was one of the places where machine learning techniques were first kind of introduced in trying to understand better the patterns of energy within these jets. And so I think Jesse Thaler will talk about this more in the talk after this. So I'm going to focus on a kind of different aspect of this, which is to try and transition this from searches to measurements. So the LHC collider, since it's at the highest energies we have, is kind of a very nice opportunity to actually study in detail the structure of QCD and the standard model. So for example, you can now produce boosted top quarks, and you can measure and study their properties or measure their mass or measure the strong coupling. And you can actually perform detailed measurements of the standard model as a field theory at energies which were not previously accessible. And so one wants to kind of transition from this kind of searches to actual first principles theoretical calculations, where you can really use this as a laboratory to study field theory. However, because of the complexity of these collisions, trying to actually compute, for example, correlations in the energy flow within these jets is an extremely complicated problem and kind of requires rethinking of how one studies jets and also the development of new theoretical tools. And so because of that, it's worth kind of taking a step back and trying to understand from a more abstract perspective what one is actually doing when one studies jet substructure. And so this was proposed about 10 years ago by Hoffman and Maldacena, or at least clearly articulated, that what one is really doing is one is studying matrix elements of what are called energy flow or ANEC or light ray operators, depending on your background, which can just be thought of as a quantum field theory definition of a calorimeter cell. And so they're actually very intuitive, that they're just some integral of the stress tensor projected into some particular direction. You just integrate over time because your detector is just running, and then you move them off to infinity because that's where the detector is. And depending on if you're a kind of collider person or a CFT person, you can either view these as some light ray operators or just literally as a calorimeter cell. And so then the object of interest that one is really studying in jet substructure is these correlation functions of these light ray operators in some state produced by the collision at the LHC. And so these essentially completely characterize the flow of energy, or if you want other charges, at infinity going off into your detector and have an exact kind of correlation with what you actually measure in the experiment. And so these are kind of a different object than most people will be familiar with, but they kind of take an intermediate position between scattering amplitudes and correlation functions, both of which have been very widely studied in recent years. And so, of course, amplitudes are very nice for collider experiments because they have asymptotic states. But the problem is they're not IR finite, and so you really have to put some little jet cone around these, which kind of goes back to this original picture I had. So on the other hand, there's been a huge progress in understanding correlation functions of local operators. So for example, in David Simmons-Duffin's talk, but these are not directly applicable to collisions at the LHC because you don't have anything asymptotically where the detectors are. And so the energy correlators are kind of a hybrid of an amplitude and a correlation function, which despite their kind of physical importance for these collider problems, have been much less explored. However, the nice thing is you can kind of borrow the techniques from each of these fields and kind of merge them to better understand these objects. And so these objects, I think, are intrinsically kind of interesting, but the reason that they become even more interesting in the study of jet substructure is that you're not interested in these kind of correlation functions where these light rays are pointed at generic directions, but instead you're interested in the case where they're all brought together within your jet. So you have kind of a jet that you cluster, and then you want to look at the flow of energy within the jet. And so in particular, when all these light rays are brought together, you're in this small angle, or what's referred to as the operator product expansion limit. And so just generically in quantum field theory, as you bring operators together, you expect to have some universal behavior. And that's certainly very well understood for local operators. And it was argued by Hoffman and Maldacena that these light ray operators satisfy similar OPE. So as you bring them together, you can essentially replace two calorimeter cells with a more general detector cell, at least in theory world. And it produces some angular scaling as you bring them together. So theta is the actual physical angle between these on the sphere. And so they kind of suggested that one could completely understand jet substructure in terms of the symmetry structure and this OPE for these light ray operators. And there's been quite a bit of work in the conformal field theory literature on developing this idea further. And so this sounds kind of like a very beautiful idea, and that one should be able to understand jet substructure just using these techniques. And so just to put a nice picture from the KITP discussions to show that these are useful when they're recorded in the future, one can look at the kind of discussion when this was first presented. And in particular, this was a talk here where Maldacena presented these ideas, and then Polchinski asked, well, there's a huge amount of QCD data, and particularly the LHC is running, you have had all these colliders, so why can't you just look for this in data, and why can't you actually do this? And so he kind of said, people don't do this, I don't know why they don't, etc. And so that has been, so this was in 2009, and unfortunately the kind of, this has not really changed since then, and so in particular, none of these correlators have ever actually been measured at the LHC. And so this is, and I can explain more offline why, due to kind of a historical accident, that people originally started studying these jets in terms of kind of shapes, which is a kind of nice intuitive picture, which was developed in the late 70s, but it doesn't really have a kind of field theory underneath it where you can really understand these things in much more detail. And so this has kind of prevented the application of all these nice theory techniques, which were developed in the conformal field theory literature to the real world of LHC. And so what I want to discuss in this talk is this kind of program to formulate the study of jets and the standard model at the LHC in much the same way that one does for studying, for example, condensed matter systems, where you measure correlation functions and their scaling behavior, and that one can really do the exact same thing and measure the scaling of these correlators as well as their shape dependence on the detector at infinity. And this really allows one to start using a lot of the nice techniques developed in these Lorentzian, which unfortunately is misspelled, CFTs to real-world collider experiments. Okay, so the most basic thing that one can try and look for is this scaling behavior, which is the same as kind of critical exponents in for local correlators. And so how does one actually do this? So as I just said, jet substructure is the study of this small angle limit. And so the most basic thing you should do is measure these 2-point correlators, and they predict that you have some scaling behavior shown here as a function of the angle between them. And so these operators, although I won't discuss them in here, they can, they're very concrete objects. They're just the leading scaling is just the twist 2 operators in QCD. And so one can really just work out the details and make this inequality and derive everything you need to understand a real world hadron collider collisions. And so what the nice thing about this OPE is it doesn't just apply to kind of 2 of these detectors, because you can just do it iteratively. You can study, for example, 5-point or arbitrarily high point correlators, and you just iteratively OPE them. And when you do this, what you get out are just some light ray operators with a particular spin, which is shown here. And so then the scaling of, for example, a 5-point correlator is just related to the anomalous dimension of this particular light ray evaluated at some spin 6. The exact details, again, don't matter precisely. I'll show this in the next slide. And so sometimes in the future slides, when I actually show the experimental results, we'll normalize by this 2-point correlator, which is very convenient experimentally and also removes some hadronization effects. Okay, so what does this actually look like in data? So this is a measurement done using CMS open data with Jesse and collaborators of this 2-point correlator of these energy flow operators. And this is in a real kind of full hadronic collision. But again, because of this universality of the OPE limit, it doesn't matter all this other stuff that's going on. And so you can really just calculate this analytically. And you see this beautiful agreement between this scaling prediction of the light ray OPE and our analytic results. And so again, I should emphasize that for people that have followed jet substructure, often you need to add, for example, grooming algorithms, etc., to kind of remove everything else that's going on. But here, just the OPE just does this for you. And so there's nothing that's been added to this calculation or tampered. And so this is really just the underlying scaling properties of this light ray OPE as was predicted by Hoffman and Maldacena. And so that's kind of a, at least to me, a kind of beautiful prediction that this is kind of a real thing in the real world. However, because of the huge LHC data set, you can actually go kind of way crazier, and you can measure, for example, up to 10-point correlators. And so these are spin 11 light ray operators, and you can see that they all exhibit this beautiful kind of scaling behavior. So now it's in this particular ratio shown here as you go from the 2-point to 3-point all the way up to 10 points. And so this really shows quantitatively this Lorentzian scaling of these light ray operators as, again, predicted by this now iterative light ray OPE. And you can read off, for example, very basic features of these light ray operators, for example, that they're convex in the, or the anomalous dimensions are convex in this spin. And so this is why this slope gets steeper and steeper as you go to higher point correlation functions. And so this is just a kind of measurement. But you can, again, look at these ratios quantitatively, and you see very good agreement. And this is something that was done very recently, so it can definitely be improved. But these are really quantitative tests of the anomalous scaling of these light ray operators, and in particular, also the value of alpha S and the spectrum of these twist 2 anomalous dimensions. And so I should also emphasize, so even if you don't like this light ray OPE, these are also just the first calculations of substructure observables, including the full normalization. So there's nothing being kind of fudged in here at this level of accuracy at the LHC. And so this is something which is quite nice. And so one can now go back and kind of answer in the affirmative that now people do this, and it works wonderfully, and you can really see all these beautiful scaling properties. And in particular, I think this is a really nice example of these ideas which were developed in this conformal field theory context for relatively different ideas can really have an impact on understanding real-world collisions at the LHC. And so scaling behavior is nice, but of course, what one wants to do is really measure higher point correlation functions. And so this is kind of like in the CMB, you start with the 2-point correlator, but then you can move to higher point correlations, which kind of encode in some way the interactions between quarks and gluons. And so multi-point correlators, as I just said, they probe in a much more non-trivial way the interactions of quarks and gluons in QCD. And so they're extremely interesting, both experimentally and just their analytic structure. And so the simplest thing one can do is to start with these, or the 3-point correlator, which is the first correlator with a non-trivial shape dependence. And so in particular, once you remove the scaling, it's a function of a single complex variable z. And so you can, for example, rescale and put 1 at 0, 1 at 1, and 1 at some complex variable z in the complex plane. And so just for people, for what I'll discuss a bit later, you may recognize that this, of course, is the identical kinematics to a CFT 4-point function. And so using this open data, one can now actually measure the structure of these correlators. So this is really the kind of shape on the detector. And so just to be able to bin this experimentally, so these triangles normally live in some overlapping region of circles, which is something that is difficult experimentally to bin. And so you can kind of blow up this OPE region into some plane using some change of coordinates. And so it's a bit hard to visualize what these are, but for example, an equilateral triangle is up here, and this is where it collapses down to a line, and then this is this OPE limit. And so you can see, for example, this is an actual measurement, again, of this kind of correlations in the energy on the detector compared with an analytic prediction. And so just for fun, so here this is for a particular scale, but you can kind of make a video as a function of scale, which is shown here. And you can see as you transition from quarks and gluons, where they have this intricate structure, through the hadronization transition, you just wash out all structure because the hadrons aren't interacting. And so you can see, I kind of see by eye in a nice video, which has some music to it, the actual hadronization transition. And so the reason why this is particularly exciting to me, and so here I'll be very kind of brief on this, is that these are real, honest to goodness correlation functions which actually live on your detector. And so it allows, even in this very complicated LHC environment, all the nice techniques which have been developed in the context of conformal field theory, even though in this context, it's still quite a basic application, but it's kind of an illustration that these techniques actually work. So for example, one thing everyone knows that you can do with correlation functions is you can decompose them into conformal blocks. And so there's an analog of this for these light ray operators which live on the sphere, which is called the celestial block expansion. And so this is a decomposition into operators which are eigenstates under the boost anomalous dimension and transverse rotations about the direction of the jet. And so you can work out what these partial waves are. In this case, they're exactly just 2D conformal blocks. And you can perform this expansion, and these are just some kind of shapes which live on your detector. And so the thing which is kind of fun is you can just see how well this converges. And so it's a bit hard to see in these plots. But this is, for example, a simulation in Pythia compared with a calculation. And then in blue is this block expansion. So at twist 2, it's a bit off, but as soon as you include the twist 4 block, it immediately converges kind of very nicely. And so this allows one to start studying these higher point correlation functions by really just expanding them in conformal blocks and using OPE data just like you would in the conformal field theory. And so though I don't have very much time, I'll just kind of briefly mention that these, I mean, ideally one would like to make this go much further. And so there's recently been a couple of papers studying the structure of the crossing equations in the large transverse spin limit for these objects. And so in particular, this OPE data is analytic in the light ray transverse spin. And you can play these standard games that have been done, for example, for 4-point correlators, but now in the language of kind of perturbative amplitudes. So for example, you have to get the same result if you do the OPE in this channel or the OPE in this channel. And so this singularity of the gluon propagator is reproduced by an infinite set of operators in this other channel, which allows you to play all these games which have seen a huge amount of interest in this analytic conformal bootstrap program. And so there was this nice Snowmass paper a couple days ago, which highlighted that this is kind of an interesting understanding the bootstrap for these light ray operators is an important problem also on the formal side. And so it's kind of a very nice collision of interest from people studying these Lorentzian CFTs and this real world collider physics applications. And so I should just say as one final slide, so ultimately I've kind of done most of this in the context of massless QCD, but there's really no restriction to do that. And one can start studying more interesting systems, for example, boosted top quarks. And so here, instead of having a perfect scaling because of the almost conformal symmetry, here you really just see the mass of the top quark imprinted into your correlation function. So as you change, for example, the mass of the top quark, you see this peak at this particular characteristic scale in your correlation function. And so this can be used, for example, to measure the mass of the top quark in a situation where you really understand how to calculate things from first principles. And so just to conclude, so one thing which I think is quite exciting for this, or for the LHC, is that this jet substructure provides essentially a physical realization of the OPE limit of these light ray operators. And so it kind of builds a direct bridge between kind of a lot of recent field theoretic work and real world QCD phenomenology. And so I showed that these shapes and scalings of these multi-point energy correlators can be measured. And so these all behave kind of beautifully, exactly as one would expect from the theoretical perspective. And so I think this really opens the door to kind of a precision program using jets and jet substructure at the LHC or other colliders. So thank you for your attention.
Great, thank you. Perfectly on time. So we have plenty of time for questions. Start over here.
This is Shu Henshao. Thanks for the really nice talk. I have a question. So do these light ray operators correlation functions, do they obey exactly the same rule as the correlation functions in an honest to God 2D CFD would?
No. So yeah. So one, if I go back, so one thing that's particularly, I didn't discuss this in any detail. If I go to, for example, this picture. So in general, like if you inserted a local operator and really measured these on the sphere, then you have to derive non-trivial new conformal blocks, and they have a completely different structure. So here, often what one is interested in the LHC is the kind of leading scaling behavior. And so here you can expand the generic conformal block in one variable, which is a scaling variable, and that essentially can be viewed as flattening this to a plane. And in that expansion, the conformal blocks are identical to those of a 2D CFT. But beyond that, it's a more complicated structure. And so in these papers that we had worked out, or I guess here, these discuss the more general structure. And so here you've really projected it to a plane. And then the nice thing is, at least in perturbation theory, then it really behaves, it has the same blocks, and it's just a function of the two complex variables, and that's why you can just kind of plug in all these nice Lorentzian inversion and everything. But it definitely a higher twist in the expansion, things are less understood.
Yeah, thank you.
Thanks for a very nice talk, Ian. Just a little historical comment, which I made you before, which is people knew the leading log behavior of the small angular correlation functions long before that 2009 discussion.
Absolutely.
It just wasn't known to the people in the room, but
Absolutely.
it was there.
Yeah.
And, you know, you might say it was E plus E minus, so I'm not going to talk about it, but it was also,
yeah.
You know, our paper was E plus E minus too, and it's the same evolution, I think, right?
Yes, exactly. So I think the point that I wanted to, so I did not include any E plus E minus just for time. Otherwise, in general, I'd have a more detailed discussion of this. But I think this point, even in E plus E minus, so if I go here, part of the difficulty in E plus E minus is they were never at a high enough energy to really study this scaling behavior in the collinear limit.
So it's not that the theory wasn't known, is that the non-perturbative fragmentation effects overwhelm you when you only have jets of order 50 GeV. But of course, the LHC is great for
and this is where you really gain with the LHC. And I think the advantage of this light ray OPE is really for studying these higher point correlators. So I mean, as you know, for this 2-point, I mean, Veneziano and friends did the 2-point, at least at leading log 50 years ago or something. And so the real kind of nice thing about these OPEs is for systematizing these much higher point correlators. And the other problem with E plus E minus, and I think, so Ellis and friends originally proposed these 2-point correlators, and they obviously understood you could do higher point correlators. But in jets at LEP, you had kind of 3 or 4 particles max. And so you can't do things like, or the fact that the particles have a finite mass makes a huge difference. And so you can't measure, for example, 5-point correlators if you only have 4 particles. And so the kind of really nice thing about the LHC, which I think should be kind of more emphasized, is you're really, I mean, these are like TeV jets with 50 particles, and so even up to 10-point correlators, you're really in a perturbative regime where everything is working beautifully. And I think that's the big gap from LEP. But yes, there's mismatching communications from both sides, which delayed things significantly. Yes.
Can I ask one technical question
too?
You said NLL prime in the. So does that mean the hard function is still leading order?
So actually, this has an extra leading order hard function.
Okay.
So that's the new, as compared to, for example, my paper with you, the main, so one just swaps in the jet function with the next leading order hard function at the LHC. So that's the main
well,
advance.
Yeah, that's a big advance.
Yeah, and that actually, I didn't show it, but it makes a difference in, you don't get the agreement I showed if you do not do that.
Great, thanks.
This is Shavik. Thanks for the very nice talk. Could you comment briefly on the BSM applications, like if there are new particles, potentially the OP structure gets modified, and one can use these sort of correlation functions to look for those?
Yes, so in very general terms, if something modified this, one could see some pattern. As compared to why this would be beneficial as compared to other approaches, I think that's less clear. And I think the main advantage of these is their analytic control for measurements. But maybe one thing I can maybe highlight where these do feed into something that could eventually be used in that way is, so one nice thing about this OPE is it in particular allows an understanding of the, although I didn't highlight it, the transverse spin of these light ray operators. And this was something that was not well understood or hadn't received much study in QCD. And so in particular, it was missing in parton showers. And so this was recently implemented by Gavin Salam and collaborators, and you could really tune that angular dependence against calculations from the light ray OPE. And then those, and so they compared their parton showers with the calculations from this. And then those parton showers can be used much more broadly once they include more effects to look for more subtle things in jets. But I think it's mostly going to be unless something is really wild looking, you're not going to see it first with these, but these can be, as you understand things better, they can be exploited more in other contexts. And I think that's the way one could most optimistically hope for them to slowly propagate.
More questions? Yes.
Just a naive question from a cosmology background. In cosmology, when we measure higher point correlators, often the hardest part is computing the error bars because the covariance is like twice as hard as calculating the correlator. Is that a common problem here? Like if you want to calculate a 5-point function, do you know how to put error bars on it?
So I'm going to be 100% honest. I personally do not. But the thing is, one has, so as compared to cosmology, the amount of data one has at the LHC is just extraordinary. And so these studies that were done here were done by Jesse's student Patrick, and this is just using publicly available open data, which is, I don't know, 1% or a fraction of the total LHC data. And even these, you can, because you just get jets in every event. And so there's just millions and millions and millions of these. And so I really, even up to like 10 points, I don't think the amount of data for QCD jets is a problem. So it's a very different situation than cosmology.
Okay, thanks.
Do you have any remote questions?
I've actually got a question, somewhat building on what you just said. This is Nathaniel Craig in response to Dan's question. So indeed, you made somewhat of a big deal that there are no actual measurements by the collaborations. You showed us a lot of nice open data.
Yes.
What sorts of things would you want to do with actual analyses by Atlas and CMS that are not accessible at the level of CMS open data?
Yeah, well, so I think one should take anything I plotted here with a grain of salt. And so so for example, in this plot I showed, I did not have, for example, somewhere I put it, there were no error bars, for instance. And so that's obviously suspicious. And it's also, so one of the things, for some of these, we can do them on tracks. And so the unfolding has a smaller effect, but these are also not unfold. There's a whole bunch of things. So this should not be used. This is kind of, should be viewed as like things are loosely speaking working. But if you want to, for example, extract like a strong coupling constant or measure the top quark mass, you need an actual measurement. And so these should be viewed as very, and same as these next ones, as very loose. So for example, this has error bars, but these are purely statistical. And of course, that's not really, that's just something one can put on. But yeah. One shouldn't take these too seriously, other than that things are in the kind of ballpark.
So maybe there's an opportunity in the Snowmass process to convey this message to the collaborations.
Yes, yes. And so people are definitely measuring. So for example, this 3/2 has been measured now very precisely in CMS, and it works because of taking these ratios is also nice, not just theoretically, but experimentally, it's extremely clean. And so this has been measured to, like, with actual error bars to very, very high accuracy. And so these should be done, yeah, properly and not just with random things that theorists have put in. Yeah.
All right, I think we'll end the discussion there. So let's thank Ian again. Nice talk.